In our previous session, we had discussed about the controls, elevator effectiveness, and the wind tunnel model. Now let us start off with elevator angle to trim, elevator hinge moment, stick force, trim tabs, and stick force gradient. Elevator angle to trim. Wing body model with wing area of 90 meters square and weight of 2.27 into 10 to the power 4 Newton, elevator control effectiveness of 0.04 and velocity of 61 meters at sea level. First, we must calculate the angle of attack for the aeroplane at V infinity is equals to 61 meters per second. So we have CL is equals to 2W by rho infinity V infinity square into S. So substituting the values of weight and density and velocity and the wing area, we get 0.52, which is the coefficient of lift. Now we must calculate the lift slope. So A is equals to VCL by the alpha is equals to 0.08 per degree. And then the absolute angle of attack is equals to CL by A. A is the lift slope of complete aircraft. So we get 6.53. Elevator deflection required to turn the aeroplane at this angle is given as Cm0 plus dou Cm Cg by dou alpha A into An by Vh dou CLT by d delta E. Now to find each and every parameter in this equation, we have Cm0 is equals to 0.06, which can be found out from the aircraft stability course as discussed. The Cm0 is equals to Cm of the aircraft wing body plus Vh is the tail volume ratio into lift slope of tail into IT is tail setting angle and E0 is the downwash angle. When the wing body combination is at zero lift, then we have Cm Cg by dou absolute angle of attack. We have the formula as A, that is the lift slope of complete aircraft, into the difference between the lift acting through the arm movement minus the tail volume ratio into the lift slope of tail divided by the tail lift slope of the complete aircraft into 1 minus dou E by dou alpha, which is the change in downwash angle with respect to angle of attack. Then we have An, which is equal to alpha A, which is the absolute angle of attack. Then we have tail volume ratio as DST by CS, and then total deflection is downwards. When substituting all the values in the equation, we get minus 1.94, which indicates that to trim the aeroplane at an angle of attack of 6.5, the elevator must be deflected upward in 1.94 degree. Hence, we have the elevator angle to trim. Elevator hinge moment. Consider an horizontal tail with an elevator that rotates about the hinge axis. First, consider the tail at zero angle of attack. The aerodynamic pressure distribution on the top and the bottom surface of the elevator will be the same, that is symmetric about the chord. Hence, there will be no moment exerted on the elevator above the hinge line. Now, assume that the tail is pitched at an angle of attack alpha T, but the elevator is not deflected, that is delta E is equals to 0. There will be low pressure on the top surface of the airfoil and high pressure on the bottom surface. Consequently, the aerodynamic force on the elevator will not be balanced and there will be a moment about the hinge axis tending to deflect the elevator upward. Now consider horizontal tail at zero angle of attack, but the elevator deflected downward and held fixed at an angle of delta E. Flap deflection effectively changes the camber of an airfoil and alters the pressure distribution. There will be low and high pressure on the top and bottom surface of the elevator. As a result, the moment will again be exerted about the hinge line, tending to rotate the elevator upwards. Thus, we see that both tail angle of attack alpha T and the elevator deflection delta E results in the moment about the elevator hinge line, such that the moment is defined as the elevator hinge moment. Here HE is denoted as the elevator hinge moment. Chord line of the tail is CT. The distance from the leading edge of the elevator to the hinge line is CB. The distance from the hinge line to the trailing edge is CE, and the portion of the elevator platform area that lies behind the hinge line is SE. The elevator hinge moment coefficient CHE is defined as HE by half rho infinity V infinity square SE CE. where v infinity is the free stream velocity of the aeroplane. The hinge moment coefficient is written as Che is equals to dou Che by dou alpha t into alpha t plus dou Che by dou del E into del E, where dou Che by dou alpha t and dou Che by dou delta t are approximately constant. The actual magnitude of these constant values depend on the elevator nose shape, gap, trailing edge angle, and platform. He is very sensitive to local boundary layer separation. Downward elevator deflection are positive hinge moments that tend to deflect the elevator downward are also defined as positive. That a positive del E usually produces a negative He, hence dou Che by dou delta E is also negative. Stick force. To deflect the control surface, the pilot must move the control stick or rather pedals. The forces exerted by the pilot to move the control surface is called a stick force or a pedal force, depending which control is being used. It is denoted as F. The sketch here is a simple mechanical system used for deflecting the elevator. The work of displacing the control stick is equal to the work in moving the control surface to the desired deflection angle. We can write the expression for the work performed at the stick and the elevator as F Ls del S is equals to He del E. Rearranging, we get F is equals to del E by Ls del S into He, where it is substituted as G, called as the gearing ratio, is the measure of a mechanical advantage provided by the control surface. Substituting these expression in the hinge moment defined earlier into the stick force gradient, we get F is equals to dChe half rho v square SECE. Already we know that He is equals to Che into half rho v square SECE. From this expression, we can see the magnitude of the stick force increases with the size of the aeroplane and the square of the aeroplane's speed. Similar expression can be obtained for a rudder pedal force and aileron stick force as well. A stick force at trim can be made zero by incorporating a tab on either the elevator or the rudder. A tab is a small flap located on the trailing edge of the control surface. It is used to zero out the hinge moment and thereby eliminates the stick and the pedal force. It has great influence over the hinge moment but has less side effect on the lift produced by control surfaces. Stick force gradient. Another important parameter is the design of a control system is a stick force gradient. The graph here shows the variation of stick force with speed. The stick force is measure of the change in stick force needed to change the speed of an airplane. To provide the aeroplane with speed stability, and stick force gradient must be negative, that is, dF by dV should be less than 0. The need of a negative stick force gradient can be appreciated by examining the trim point which is shown on the graph. If the aeroplane slows down, a positive stick force occurs that rotates the nose of the aeroplane downward, which causes the aeroplane to increase its speed back towards the trim velocity. If the aeroplane speeds the trim velocity, a negative stick force causes the aeroplane's nose to pitch up, which causes the aeroplane to slow down. The negative stick force gradient provides the pilot and the aeroplane with speed stability. The larger the gradient, the more resistant the aeroplane will be to disturbance in the flight speed. If an aeroplane did not have speed stability, the pilot would have to continuously monitor and control the aeroplane's speed. This would be highly undesirable from the pilot's point of view. I hope you would have understood today's session. Let us start off with directional control and roll control in the next session. Thank you.